Now we are trying to visualize the stress transformation equations. The best tool for this is known as Mohr's circle. Let's start with a single surface on which we find a normal stress and a shear stress. We want to call the normal stress sigma and the shear stress tau. So that's consistent with what we've done in class. There is one little difference. I want to look at a single surface and I need to enhance our sign convention. I'm using normal stress as in class, tension positive, and a shear stress shall be positive if I take the normal stress vector and rotate it counterclockwise. That's my positive shear. Next, we are using a coordinate system in which we plot horizontally the normal stress, vertically the shear stress. The peculiarity in this is historically driven that we draw positive shear downwards, and we can interpret that as a counterclockwise rotation of the normal stress to shear goes down, a clockwise rotation of the normal stress towards shear goes up. Sign convention for normal stress is easy. Positive is tension, negative is compression. Next, I pick our stress block and try to see how a stress block fits into that picture of Mohr's circle. First, note that a stress block has 4 faces. So Mohr's circle draws 1 point per face, and I simply start with the first face. So that's the one perpendicular to X, the positive face, and I want to draw the stresses that we have using the sign convention from our stress block. So I see sigma X and tau XY. Next, I want to use Mohr's circle sign convention that we just introduced here in green, and I draw my positive normal stress, and the positive shear stress is take that normal stress and rotate it counterclockwise. Now I compare the two sign conventions and they are in perfect agreement. We see that the normal stress is plus sigma x and the shear stress on that face is plus tau xy. Now I can go in my coordinate system and I just assume some values for that demonstration, and I have a value for shear tau xy, and I have a value for my normal stress, in this case sigma x. Now that I have the coordinates, that means in that diagram that will result in 1 point. That point I just mark it as sigma x is the first component is sigma x, the second component is tau, which in our case is plus tau xy. This 1 point represents that phase. Next, we need to look at the next phase in our stress block. So how about we take the surface y is constant. So that's this blue surface. On that surface, the stress block has a normal stress of sigma y, and it has a shear stress of tau xy. In red, I draw the positive components based on the stress block. Next, again, I switch to green to show positive normal stress according to Mohr's circle sign convention, and positive shear stress tau, that's simply the sigma counterclockwise rotated by 90 degrees on Mohr's circle. So if we compare now, the value normal stress sigma agrees with plus sigma y, but the positive Mohr circle shear stress goes the opposite direction. That means it's minus tau xy. In that diagram, we draw what I marked as green values. So now we have the shear stress is minus tau xy and some normal stress sigma y. Again, we have coordinates of a point, and if we enter that point, we see that the sigma and tau coordinates are plus sigma y and minus tau xy. The next step is to ask which other locations could we find on that diagram if we now start applying different coordinate transformations. And Mohr showed that the stress transformation equations in that diagram turn into a circle. The center of that circle is found by simply making a straight connection between the two stress points that we found from the stress block, and that line intersects with the sigma axis at sigma m. That's just the mean stress. And we see that on both sides we have the same distance, which I want to call r, from the center to the stress point. If we draw a circle through that center point at sigma m, then this circle represents all possible stress states. Think of it, any point on the circle represents one pair of normal stress sigma and shear stress tau, and each of these points is associated with a surface. Next, we are asking the question, what could the largest normal stress or the smallest normal stress be under any transformation? And for this, we look at our Mohr circle, where the circle represents any possible result that the stress transformations could provide. If we start looking at that circle, we will see that there's a clear maximum and minimum along that circle, and these maximum and minima, they are actually located on the sigma axis. That means maximum normal stress, we call them sigma 1 and sigma 2, come on surfaces where the shear stress disappears. Computing these values is simple from the circle ahead. We simply find the values sigma 1 and sigma 2 as the center of the circle plus minus the radius. So sigma mean plus minus the radius. The mean value sigma m is really just the mean of the two normal stresses on our stress block. That means the mean value sigma m is sigma x plus sigma y over 2. So that's the cheap computation. The radius itself isn't very difficult if we find that marked area here, and we see this is sigma x minus the mean value, and we have the second side of that triangle as the shear stress tau. That's a standard triangle, so the radius r follows from the Pythagoras theorem as sigma x minus sigma m squared plus the shear stress tau xy squared, square root thereof. That's a very simple relationship. I typically like working this from Mohr circles. That way I don't need to remember any complicated equations. All I need is an average value and a triangle equation.